fatigue life. Okay, it looks like this presentation is a little bit, sort of, but okay, I believe it will work well. Okay, so this presentation is about practical use of finite element method in evaluation of fatigue life. And since I'm coming from Department for Aeronautics, so in my focus are mostly problems from aircraft design, from aircraft industry, and very often different firms are coming to me to solve some problems related to fracture, related to fatigue. In this case, we had a problem with this aircraft Cessna 172S, which is the most successful aircraft in the history. More than 45,000 units have been produced in 65 years, and this is still the best seller in the world. The main thing about this aircraft is it's designed in 1950s. So first model was built in 1955, and we're still using almost the same structure, almost the same components, of course with some improvements over time. So idea here was to evaluate fatigue life of one very critical component. We will see that on the next slide. And for that purpose we used, of course, stress intensity factors approach based on evaluation of SIFs through incremental crack growth, and then using classical Paris law to evaluate the fatigue life of that component, and then to compare fatigue life with improved or optimized components. So this conference was supposed to be in 2020, right? But it was cancelled due to coronavirus. So in the meantime, we did more things. So now it's my pleasure to present more things than in 2020. Okay, so this is that critical part. It's called torque link. The torque link consists of two parts: upper torque link and lower torque link. And this is the part where cracks usually appear. You can see here in this area. And the recommendation by manufacturer is to replace this part with spare part or a new part when length of the crack is approximately 4.5 millimeters. So this was for me also interesting how they in 50s and 60s how they evaluated that fatigue crack life. I mean crack length. They didn't have finite element methods. They had only analytical and practical approach. So this was a challenge for me because I wanted to see why that length is critical, number one. Number two, to try to improve with modern numerical methods to improve design of these methods. So this was challenging. And yeah, this is basic theory. Because we use ANSYS workbench for stress intensity factor calculations. So this is a formula for interaction integral. Probably all of you are familiar with this formula. And this is the interaction integral connection with stress intensity factors through this. This is what is built in. And of course, I mentioned before that we use here Paris law, but also it's possible to use other laws like the Walker equation or Foreman or Nasby equation. Also, you can write your own code in Python and use your own crack propagation law based on your experimental data. Okay, so basis for this calculation was this experiment that we carried out 4 or 5 years ago. This is CT specimen made of aluminum. Aluminum is material used in aircraft design mostly, but that part was made of stainless steel. So we used this experiment only to define mesh settings, to see what is the best mesh, since it's 3D simulation, to find the best mesh settings that can help us to get, let's say, reliable results. And here, this is the presentation that I wanted to show 2 years ago that we, successfully maintained to carry out this simulation, got results which were in line with experimental results, and number here of cycles obtained in finite element method, and number of cycles in experiment were very close to each other. Difference was something like 5%. We use here changeable load during the experiment and use changeable load in a simulation. So this is the model of torque link. Next step was to define geometry, to apply boundary conditions, load and everything else which is necessary. And then we get here deformation and stress in the area where usually cracks appear. And this is where, of course, we initiate that first crack and then carry out the simulation, which can be seen here in this video. And the maximum crack length in this simulation was about 4.86 millimeters. We evaluate the stress, we evaluate the number of cycles during arbitrary Paris coefficients. Why arbitrary? Because we don't have data for this stainless steel. I mean, we contacted the manufacturer, but usually you cannot get this info. They told us it's just stainless steel of that, I mean, class and so on, but we don't have data for that. So then you're thinking about this. Okay, can we change this structure, optimize it, since we can see in the previous slide that most of this here area is not under stress. I mean, stress is very low, and definitely some material here can be removed. So we continued with topological optimization, and we did several studies. This is study number 1, where here we kept some of these red faces here and then tried to eliminate other material. Got something like this, where deformation was slightly higher, stress is slightly higher than the previous, and again the same. I mean, under the same loading conditions, we got the same area with crack initiation. In the second case, we kept this here area because it's important for other part for assembly to be established, and then again we got here an area with the same, I mean, almost the same stress. Here, a mass reduction in this case was around 44.6%, and in the previous case it was around 36%. So you can see here mixed topological optimization with crack simulation and fracture mechanics, I mean, simulation. So then we carry out crack growth simulation in these two optimized, let's call them optimized structures, in case study 1 and case study 2. And in that original model, we got around 92,000 cycles with the same Paris coefficients, while here we got 82,000 and 78,000 cycles. Next step was to, since idea was to print this model using 3D printing techniques and additive manufacturing, again trying to combine these, let's call them cutting edge technologies. So it took us a while to get these simulations for additive manufacturing process. For this simulation, around 1 month to, I mean, adjust all parameters so this part, optimized part, can be printed, and also to get, I mean, the shape which is reliable and can be obtained in 3D printing. For this shape, of course, we carry out all these analysis of the influence of the temperature on residual stresses and so on and so on. And finally, we came with this shape, which is definitely printable, with crack which is initiated here, and then carried out the same, I mean, simulations where the crack growth in 3D printed part, and then obtain numbers such as, in this case, we extended this crack to critical length, and that critical length is somewhere around 9 millimeters, and got to this number of cycles. So now finally let's compare all these 4 models: initial model, then case 1, case 2, and finally this model obtained by simulation of additive manufacturing. So we can see that definitely initial model here, and I mentioned before that they said that it should be replaced after 4 millimeters, and we can see that in all these cases, I mean, critical crack length was not reached. If you look at this line for 4 millimeters, and you can see that the critical growth is, let's say, when crack is around 6 to 7 millimeters. So it's definitely very important to replace this part when crack length is less than 4. And then comparing number of cycles, we can draw conclusion that difference in number of cycles varies from 8 to 18% compared to original initial model. Finally, conclusions. So definitely, we tested this, and this smart technology enhances workbench really, I mean, gives good predictions for crack growth path, because all these crack, they grew in direction which we observed in reality. Then optimized structure has shorter fatigue life, but we managed to decrease the mass by 48%, which is crucial in aircraft design. Then, of course, we used arbitrary Paris coefficients just to get number of cycles for comparison. So that was all. Next step is to, and we already prepared the CT specimen of stainless steel plus complete model printed in the 3D. And I hope next conference I'll show you results of these experimental, let's call this verification of numerical results. So thank you for your attention.
Thank you very much for the interesting presentation. Is it open for questions? Yes?
Can we use this smart technique for the non-homogeneous materials?
For
non-homogeneous materials?
At the moment, no. So it's limited only to tetrahedral elements. So maybe you mentioned that for first model I used hexahedral elements, but later for simulation of Grbović only tetrahedrals. So at the moment only, okay, I put that on our presentation, but didn't mention only linear elastic fracture mechanics can be used. So only in homogeneous materials, so not in non-homogeneous. No. At the moment, no. I mean, most of these presentations I saw today were about, these fundamental things in fracture mechanics, simulating in a 2D, simulating on a grain boundary level, things like this. But at the end of the day, we have to use this in the practice, and I think this is the, application of this is also very important for all of us.
Due to additive manufacturing, do you have some kind of anisotropy in the fracture properties?
Yes.
And did you include it?
No, not yet in the model. Not yet in the model, but that's next step.
Okay. Thank you very much for the presentation.